mixed words up occasionally. But being able to re-listen to it. Yeah.
Is it 12:30 officially yet?
I think so.
My watch is a little fast, so. Well, good afternoon. Welcome to another Chem 401 lecture. Where were we? We had just, did we talk about this one last time? Or were we on the last one?
You guys.
Oh, we did this one, we did that.
Yes,
That's where we are.
C.
Oh, right. So on the one before, I gave you a problem and I set it up. I will post the answers to that. But for now, let's go ahead and go on to this example. I apologize for the configuration change today. I'm going to be writing down here while most of the content's going to be up there. I forgot a cable, and so I couldn't connect to my card over there. Anyway, well, let's get down to it. I guess a couple of announcements. All the homeworks are now on the Chem 401 website. Your homeworks will be due in the following order. 1 week from today, the electrochemistry will be due. 1 week after that, the transition metals will be due. 1 week after that, go ahead and get them later, please. Yes, they'll be here. 1 week after that, the nuclear chemistry will be due, and nuclear chemistry will be due on the day of your third exam at that point. And then, on the Monday before the third exam, you'll have one lecture on organic chemistry, and there will be a short homework which will be due at the final. All those homeworks are available to you on the website, and 2 of them are up here, so pick them up on your way out. Or download them from the website. Let's see. Yeah. So, well, where were we? We were talking about electrochemistry. We'd done an example on the previous page in which we do what I call electron bookkeeping. That means you use the half reactions in the oxidation or reduction half reactions to do stoichiometry. For example, in lead 2 plus 2 electrons goes to lead solid. For every 1 mole of lead 2 plus, there are 2 moles of electrons. That becomes a unit conversion. So I have an example here. In the lead storage battery, usually found in cars, the battery delivers 1.50 amps and starts with 1 pound of lead. How long can the car run before it runs out of lead? Well, this is a question we can ask. The car will not last this long, by the way, but we'll pretend. We've got a balanced half reaction right there, and it shows that for every 1 mole of lead solid, there are 2 moles of electrons. We're starting with 1 pound of lead. And I'll use LB for pound here. This works better. Well, we'll see how it goes. So since we have pounds, we're going to convert that into kilograms for every 1 kilogram. There are 2.20 pounds. Not a conversion factor we use too often, but there it is. We're going to need to go to grams of lead before we can really do the stoichiometry that we're used to. Then, using the numbers from the periodic table, 1 mole of lead is equal to 207.2 grams. Now we get, now we get for every 1 mole of lead, there are 2 moles of electrons. And for every 1 mole of electrons, using Faraday's constant, there are 96,485 coulombs. That will give us a number of coulombs. As you might guess, with that many unit conversion problems, that many units to cancel out, I'm a little excited about these prospects. I love canceling my units. But what we get there is we get 4.2 times 10 to the 5th coulombs. And then amps times time equals coulombs. We have our coulombs, we have our amps. We're going to solve for our time. I will rearrange this. Didn't even check my notes to do that. Oh, I did that wrong. That's why I should check my notes. Oh my God. Let's try that again. There we go. And the time here is going to be in seconds. I get 2.8 times 10 to the 5th seconds. And it doesn't say this, but I'll convert it into something maybe a little more familiar. I'll convert it into hours. And it turns out to be 78 hours. Now, has anybody ever left their, do cars even leave their lights on by themselves anymore? Some, yeah, so how long have you ever left your car on and come back and the battery's been dead? All night? Usually for a couple hours is all it takes before my battery is dead. And that just means to say that you're not running out of lead. If you ran out of lead, it would take 78 hours. There are other issues involved in why your car battery goes dead, not running out. Any questions about this? Yeah, Travis.
Just in the general respects to a car, do you happen to know how much energy the alternator is putting back into the battery?
It's a good question. I don't know how much energy the alternate. Well, so
it says on the sticker of each car, actually. If you look in the hood.
Okay, good. Thank you, Esperanza. That now I'm going to go look. Any other questions? Okay, so there's another example, and we're not going to do it. I will post the answer to that example. We are going to switch gears and move on to transition metal chemistry. And the main point of doing transition metal chemistry, why we're doing it in Chemistry 401, is to understand why transition metal complexes are oftentimes colored, meaning green, blue, and for those of you who have done the lab already, you've seen some of the colors. For those of you who will do the lab this afternoon, be prepared to ooh and ah, and then take lots of data about the colors. Now, where we're going to start is Electron Configurations review. So we're going to do it for chromium first, and I'll write these notes down here. For chromium, we're going to talk about a chromium atom. And we're going to do an electron configuration. And first question, how many electrons does a chromium atom have? It has 24 electrons, 24 protons. Atoms have the same number of protons and electrons. Sound vaguely familiar? Yes. I know this. So 24 electrons, and then according to, and this is why we do review, right? So according to the shape of the periodic table, we start with the electron configuration. We'll do the whole one this time, but then quickly we'll go to noble gas cores, 1s2. And 1s2, that takes us to helium, ding, go back to lithium on the other side, 2s2, 2p6. Those are the same electrons as neon, ding, return to the other side, 3s2. 3p6. And according to the shape of the periodic table, we next do 4s2, and then for chromium, 3d4. Is that correct? According to the shape of the periodic table, yes. But when I see 4 right here, I think that that's one of the exceptions. And can anybody tell me what happens? Jessica?
The one from the S moves to
The one, that's right. The one from the S moves over. And we have 4s1, 3d5. Next question by way of review. 4s or 3d, which of those sublevels is really lower in energy? 3d is lower in energy. So this is according to the shape of the periodic table, but 3d is lower in energy. That will come into play when we do our CR3 plus and CR6 plus. That's an R. When we do our chromium 3 plus, that's going to be take away 3 electrons. The first electron you take away is the 4s1 electron. Then you're going to take 2 more of those. It turns out probably you'll get the same answer anyway. And now we'll move to noble gas cores. Remember, a noble gas core is an abbreviation for the previous noble gases electrons. That will be argon with 18 of those electrons. We took away 1 of these electrons in 4s1. We're going to take away 2 of these electrons and be left with 3d3. Any questions about that? If not, then we'll do chromium 6. Take away another 3 electrons, you're left with just the electrons of argon. You can do similar things with iron. I'm going to skip this one and move on to the next slide. And talk about placing electrons in orbitals. Now we're going to do the iron atom. For the iron atom, it will have the same 18 electrons as argon. Four s2, 3d6. And it's the d orbitals that we're going to be mostly interested in when we talk about this. And so let's think about the d orbitals, specifically the 3d orbitals. How many 3d, or whenever there's d orbitals, how many orbitals are there? 5, right? 5 orbitals, and we always used to draw them next to each other, and that was meant to indicate that all 5 of them had the same energy. They were energy degenerate, if you will, or degenerate, or there was an energy degeneracy, which meant they were all had the same. So as we put them in, 1, 2, 3, 4, 5. And a rule was always put 1 electron in each of them before you pair any of them. There was another rule that said make them all spin up or all spin down, and then start the other way. Now, does anybody remember the definition of paramagnetic versus diamagnetic? Paramagnetic, did that have unpaired electrons or all paired electrons? It's a little confusing because paramagnetic means at least 1 unpaired electron. And dia, what I think of as dia means 2 electrons. It means all the electrons are paired. So the iron atom is paramagnetic. And then we want to say something else about these as well. When a substance is paramagnetic, yes, it has at least one unpaired electron. Also, it is attracted to a magnetic field. Diamagnetic, on the other hand, all paired electrons. That actually makes it so that the substance is repelled by a magnetic field. And as you'll see, these properties will be important to know as we go through the transition metal complexes, because they will provide information about how the electrons have entered the orbitals. Any questions about this? Okay. I present to you the D orbitals. And if you remember from Chem 400, if you were here last semester with me, what I said was, and if you didn't, then definitely pay attention, you have to know about what the d orbitals look like, but I wasn't going to ask you to draw any pictures of the d orbitals. That goes the same here. So you should know about what they look like, and you should recognize when you see one, but I won't ask you to draw any, well, let's say this. I won't ask you to draw any from memory. If I draw you a picture and then say do something with it, that's fair game. And that's part of what we're probably going to be doing today and throughout. So just as a reminder, you have the pictures. We don't even necessarily have to know these designators as well. Yeah, not so good. Reintroduce them. Now let's talk about coordination compounds. Definition, compounds in which a transition metal atom or ion is associated with a group of neutral molecules or anions by coordinate covalent bonds. For our purposes, a complex ion. And so I have two of these complex ions right here. You can see they each contain transition metals, and these both have ammonia in them as a neutral molecule. Right, and we'll see some anions coming up as well. Now, I'm going to be talking about the silver up there. And the way that that complex forms is you take a silver ion plus two ammonia molecules. The silver ion, if you'll remember, will be something called a Lewis acid. We talked about that a bit last semester. And the Lewis acid, the definition was that a Lewis acid accepts an electron pair. Ammonia will be a Lewis base. Ammonia is always a base, and now it's a base again. A Lewis base donates an electron pair. And they're going to make our complex ion. And form bonds, covalent bonds. And there's actually two ways to designate this. So sometimes we just put the plus at the end. Sometimes we put the whole thing in square brackets. And so you should be familiar with seeing each of these. And whenever you refer to a complex ion like this, it'll be okay to refer to them in either of these ways. And this species is called a Lewis acid-base adduct. And this term, Lewis acid-base adduct, is not something you have to remember or that I will ask you about. I can ask you to identify the Lewis base, and I can ask you to identify the Lewis acid now. And, yeah. Similar idea down here with the copper. I'm not going to go over that. Any questions? Now, the term for this Lewis base, we're going to come up with a new term. It is ligand. A ligand is a small molecule or ion that donates an electron pair to the metal. Examples: ammonia, carbon monoxide, and chloride ion. I've already drawn ammonia with its pair of electrons right there. If we were to do a Lewis structure, you would see that the nitrogen has that pair of electrons. Nothing new there, actually. For carbon monoxide, Lewis structure looks like this. And it turns out that it's the carbon that donates the pair of electrons. And so when you see pictures that have carbon monoxide as the ligand, you will see the carbon closer to the metal ion. That's because that is the pair of electrons. And for ammonia, it's pretty easy because there's only one pair of electrons that is not participating in a bond, but there we go. Carbon monoxide is the carbon. Cl minus, there are 4 pairs of electrons. It doesn't matter, just so one of them. Ammonia, carbon monoxide, and chloride are called monodentate ligands. Monodentate ligands. One of the many things I love about chemistry, certainly over biology, is that when you see a term like monodentate, well, you know what mono means. It means one. And whether you know what dentate means or not, it sounds like dentist, which makes you think of teeth, and it turns out that dentate means tooth in this example. Or that's how we're going to interpret it anyway. And so it's a one-tooth ligand. That means that when there's one pair of electrons, it takes its one tooth and it forms one bond with the central metal and a cation. Ethylene diamine, the ligand that you use in lab this week, is a bidentate ligand. It has a structure like this. It has a pair of electrons from each of the nitrogens. The only thing missing now are the hydrogens, and I'll fill those in as well. And it is, for ethylene diamine, it is each of the nitrogens, each nitrogen has one tooth, the whole molecule has 2 teeth, if you will, and it takes 2 bites out of the central metal cation. Any questions about this? I'll erase some of the stuff up here so we can talk about heme. Heme is pictured right here. Heme is over here. It's a pretty complicated molecule, but it is shown right here, taking 4 bites out of the central metal cation. Central metal cation, typically Fe2+, that's what the 2 Roman numeral means. tetradentate? Because it's taken 4 bytes. And 4 bytes means 4 bonds with the central metal cation. Question?
Can you go into like the, keep using the word byte? So they are the bidensity, or they are taking away the electrons, or they are.
Yeah, no, so what do I mean by that? I mean that these 4 nitrogens are taking their pair of electrons and using it to form these bonds. So if we go back to the last slide, so a Lewis base donates a pair of electrons. Heme donates 4 pairs of electrons, 1 for each of these nitrogens, to form 4 bonds. Right? So if the question is, where do these electrons come from? To form the bond, they come from the nitrogens. So 4 bonds is what I mean by 4 bytes. They do go up to at least 6 bytes, so hexadentate. I think I've even seen some octadentate ones as well. But most of the ones are, well, heme I think is an interesting one that goes up to 4. I think we put heme on one of your homeworks as well. All right. Now I'm going to define a term called the coordination number. Coordination number is the number of bonds between the metal ion and all ligands. So coordination number is right here. Though other geometries exist, there are 3 main geometries that we work with in Chemistry 401. So I cannot write on them, but you might want to star tetrahedral, star square planar, and star octahedral. So those are going to be coordination number 4 for tetrahedral, 4 for square planar, and 6 for octahedral. And octahedral from Chem 400, we're used to a central atom with 6 things around it having the octahedral geometry. For tetrahedral, 4 things around the central atom, also fine. What's new is there is an option for square planar, as we'll see. You'll also notice that the hybridizations, at least for 6 octahedral and tetrahedral, are the same, and the new one is square planar, which is over there. And there's examples over here, and we're going to do more with these examples. Yes. First example, cisplatin. Anybody ever heard of cisplatin? It's an anti-cancer drug, and it has square planar geometry. So let's talk about what that means. Now, so like so many things in Chem 400 and Chem 401, it can help to have a process to think about these things. And so my process is going to start with, let's look at the metal or the transition metal atom. So it's a platinum atom. And do its electron configuration. Then we'll move on to the platinum ion. And we'll talk about that. It turns out that there's a platinum 2+ ion in there. And we'll move on from there. For platinum, here we go in the periodic table. There it is, number 78. What we might do is we might abbreviate for the electron configuration. The first 54 electrons for xenon. And then 54, 55, 56, 6s2, then drop down to 4f14, then come back up and do 3d, 4d, 5d, 5d8. And that's what we'd expect from the shape of the periodic table. And what we said is that as you get down towards the bottom of the periodic table, sometimes there are small differences from these that may or may not make sense. So as you get down to the bottom of the periodic table, always look up your electron configurations. And it turns out that this is a case where there is a slight change. That makes no sense to me, but that's, that's what sometimes happens. It is 6s1, it is 5d. Now, within that though, where are the highest energy electrons? In which sublevel? It's always the highest number of n, that's right. And so as I make the platinum 2+ ion, I'm going to take first this electron and then one of these. Or F14, 5d. Now, if your question is, how did I know that it was platinum 2+? So I would suggest that we have 2 ammonias, those are neutral, and we have 2 chlorides. Chlorides are negative, so since the chloride ions are negative, to have no charge on the entire species, platinum must be 2+. Question?
So, like you said,
Yeah.
you didn't know to cancel off the 6s electron. Are we going to have examples like that, or like you said, look it up? You mean like Google it?
Good question. Okay, so let me go through the process. So what I said in Chem 400, and it still applies to Chem 401, is that if you have to do an electron configuration on an exam, it will be according to the shape of the periodic table, unless it's the chromium, molybdenum, or the coinage metal. So the same 5 exceptions apply to Chemistry 401. And if you didn't have me for 400, let's talk and make sure you're on the same page. So if there was a platinum atom on your 3rd exam or the final, I would have to give this to you. And then I could say, well, what's the electron configuration for the ion? Because that follows all the same rules.
Right.
So
Yeah.
yeah, so you will be able to do the shape. If there's an exception, I would have to tell you.
Okay.
Yeah. Because I, as you probably have guessed, I don't want you to memorize all the electron configurations on the off chance they'll be on your exam. We're all about process here. Any other questions about that? All right. So next, let's take a minute. And just think about this complex ion here. So what can we say about this? Well, first of all, the coordination number is 4. And the coordination number is 4 just means there are, like, you can either say, I guess there are 4 attachment points. We can't say 4 ligands because some of the ligands can be bidentate or more. Coordination number is 4. And our 4 attachment points, or our 4 ligands in this case, are 2 ammonias and 2 chlorides. And in this particular case, they're all monodentate. Now, what does it mean to be square planar? Well, even though this is a new type of geometry, it describes itself very well. It's in a plane and it's square. So you can put your platinum 2+ in the middle. And then there are various ways to do this, but the easiest way to do it is to draw it in the plane of the board. There are ways to draw it, and we will have to draw some out wedges and some back wedges in future examples, but not for this one. So 4 ligands attached with covalent bonds. Now, before I draw in the ligands, I'll ask you to note the word cis. Does anybody know what cis means versus trans in anything having to do with chemistry?
Cis is same side.
Cis is same side. I think of it as C as closest. That's another way of doing it. Some people say cis is the first letter of the word, or C is the first letter of the word cup, because sometimes they look like cups as well. Now, what that means though is put them closest, put them on the same side. Put the ammonias, and when I draw my ammonias, I'm going to draw the nitrogen closest to the platinum because that's what bonds. And even if you draw the hydrogens off to the side, make it look like the nitrogen is what's bonded. That will be easier for me to understand. Although, yeah, probably I don't know if I'm not. So this angle, 90 degrees. That's the square part. The planar part is it's an entirely flat species. Okay. Let me see what else. And we'll talk more about this. But for square planar complexes, the hybridization on the previous page was listed as DSP2 or SP2D. Typically, or many times, it's actually DSP2. What does that mean? That means, for this particular one, you see this 5D? You see how there are 8 electrons in it? This is where things get weird. All 8 of those electrons, when we get to talk about this, will be in 4 of the orbitals. And one of the 5 d orbitals will be open. And we don't know why that is yet, but we'll get there. So this one of the 5 d orbitals has no electrons in it. So that the ligands can form bonds with the DSP2 orbitals. Wait a minute, I forget what I said now. So that the ligands can bond with the hybridized DSP2 orbitals. Because now we're thinking about 2 things. One is the electrons in the d orbitals for platinum, and the other is how does it hybridize to bond with the ligands. Anyway, I have not explained why that is yet, but that is what happens here. Let's see. Any questions? All right, we're in the middle of the story, so maybe, well, let's see if some of those, yeah, that's what we have to say. All right, so now let's go to the next example. Yes. Okay. I'm going to erase some of this, keep some of this up here. So let's see if we can fit this example over here. So this is iron with 6 water ligands attached. It's a complex ion and has an octahedral geometry. So, coordination number is 6. There are 6 water ligands. Now, to draw 6, you do have to use out wedges and back wedges. I have 2 on this side. This out wedge means the ligand or the bond is sticking out of the board. This back wedge means it's going back. There's 2 more on the other side. And technically, these 4 are in the same plane. So that's totally flat here. One sticking straight down, one sticking straight up. It is the oxygen that is donating the pair of electrons, so we will always put the oxygen closest. Excellent. Okay, so now we've done some of the shapes. I think we're ready to move on to the next part of the story. In the next part of the story, we talk about what's called crystal field theory, or CFT. Crystal field theory can explain the colors of transition metal complexes. Crystal field theory is a model of the electronic structure of transition metal complexes that considers how the energies of the d orbitals of the metal ion are affected by the interactions with the donated pairs of electrons of the ligands. And hopefully, in a lecture or 2, it will sound less complicated than that. Okay, so we have 2 things going on here. Let's start here. These circles are the ligands represented by dots. And so if we were to say, and it's octahedral, so let me redraw. There we go. So, the metal, so these are the d orbitals, okay? And these are the ligand points surrounding them. And what's going to happen is, do you see these d orbitals? It's a rhetorical question, I'm sure. And then you see how close the ligands are? The ligands represent a pair of electrons bonded, and they're negative. So when you put electrons in the orbitals, those are negative electrons as well. Basically, the closer they are, the higher in energy they're going to be. And the farther they are, the lower in energy they're going to be. And crystal field theory is the act of thinking about the position of the ligands with respect to the d orbitals. So these dots are like the H2O and their pair of electrons. And these are the different d orbitals of the iron 3+ ion. Question, Travis?
Why is it called crystal field theory?
It's called crystal field theory. So we're looking at that's a good question.
I was just like, does it have to do with like crystalline structures? Like
So these are not crystalline structures. Well, no, because they're solutions. Well, I know why it's called a field, because you've got charges interacting. Crystal field, well, it turns out that you can see, like, we're going to be dealing with solutions, but these same materials are colored in the solid phase, and so they can be crystals as well. I'm not sure if that's the meaning of it. It's a good question, though. Now, so the first thing, though, is you have a splitting of the d orbitals. The next thing is that when there's a splitting, these are the ones, the d orbitals, that are farther from the ligands. And they're lower energy, thank you, because they're farther from the ligands. And then the ones higher up are higher energy because they're closer to the ligands. And one of your homework questions for this chapter says, actually draw some of these and draw them closer and farther as you would expect for the different shapes. Okay?
So even the y-axis perpendicular to the d superscript 2 up top to the right?
Yes.
That's even more higher energy, even though the two ligands on the x-axis are further away from the orbitals?
Ah, yes. So these ones are further away, but look how close those are.
So it makes up for it.
It makes up for it. So you can see that these two are close here. This one has all four of them close, it's true. And then this has none of the lobes as close. Yeah. And so that detail about how the exact size relates, I'm not worried about. Right? All I want you to know is these are farther away than this. Okay? And what it'll turn out is you'll have the splittings, so you'll know which orbitals are lower in energy and which orbitals are higher in energy, and then you'll just be asked to draw them. Right? I've also said that when you draw the d orbitals, I will give you pictures of the d orbitals as well. So I don't know if that answered your question. So I don't think that does answer your question, but it did. Yeah, enough, yeah. Let's see. Oh, and then these are symmetry groups that when I took this picture, it was from an advanced inorganic chemistry site. And so we don't need to know those either. What do you need to know about this is you need to know that there are lower energy and higher energy orbitals, and that this splitting of the d orbitals, that's what it's called, the splitting of the d orbitals is because of the positions of the ligands with respect to the d orbitals. That's what we need to know. And we have more to know, but that's what I guess we need to know from this picture. So this is a picture of energy for these. These are the 5 ones. And as you bring the ligands in, the ligands are negative charges. That means that all the orbitals for the electrons, which are also negatively charged, are higher in energy. But again, I'm not too worried about this part. It is true, I'm worried about this part. Okay. And this is the splitting for octahedral. Now when you get a different shape, like on the next page, you get different splittings because there's different orientations. Oh, sorry, we're not to the different ones yet. Let's do this one. It says, what is the shape and electron configuration of nickel with 6 ammonias attached as ligands? It has 6 ligands. There's only one shape with 6 ligands. What is it? It's got to be octahedral. So that part is just reproduced from the last slide. Now, let's talk about the electron configuration. Oh, so let me write that. So it's octahedral. That's 6 electrons. But we probably knew that because it's got the octahedral picture here. Now, I see that my nickel is nickel 2 plus. My ammonia is a neutral molecule. Therefore, the 2 plus charge is associated with the nickel. I do my electron configurations. Well, all you need for this is the electron configuration for nickel 2 plus. I always do the nickel atom first. Nickel will be argon 4s2 3d8. Nickel 2 plus. Argon 3d8. That's important because we will be putting the D electrons into the orbitals. You've got this picture, but since the top goes off the page, I'll redraw it down here for me to put in the electrons. Here they go. 1, 2, 3, 4, 5, 6, 7. So you'll need to know how to do your electron configurations for the atoms and the ions specifically, and then you'll have to put those electrons into the orbitals. Last thing, I'll point out that little symbol right there. It is delta O, or delta naught, and it is the crystal field splitting energy. Yes?
For the nickel atom, have you ever taken the 2 electrons from the S and bumped them over to the D?
So question, could I have bumped these 2 electrons over and made 3d10? The short answer is no. The slightly longer answer is that this is the right answer. And the only time we ever saw exceptions to the rule for the shape of the periodic table was for at most 1 electron. And right, the bigger picture goes back to this whole debate about 3D versus 4s. They're close in energy, and every time we get another proton in the nucleus, 1 more D electron can fit in. Anyway, there was a whole, but in the end, the short answer is it only ever happens to 1 electron.
Okay.
Yeah. Good. So the wavelength of light associated with DO, well, that should be my delta symbol again. I apologize for that. That's delta O, is often in the visible range.
That's delta O, not delta naught?
Delta naught, yeah.
Okay. Because that looks like a 0, and so
I
I'm
did
like,
make it a 0,
okay.
yeah. I'll have to think about that. Let's just call it delta 0, because I always made it a 0. I always think of naughts at the top.
Yeah.
I don't know. I have to think about why it's a 0 or whether it's a naught. So here's what I want to do with this. So I've got, from the previous slide, I've got my 8 electrons. I'm going to add a frequency of light, and I've written it h times the frequency because that's going to be equal to energy. And what happens is when we add energy to this, one of the electrons gets promoted to the higher energy as the light is absorbed. One of the electrons gets promoted to the higher energy level D orbitals. As the light is absorbed. And of course, this is an excited state because the electrons are not in their lowest energy position. And the electron quickly comes back down. But for our purposes, the light has been absorbed. And we're going to measure that light that is absorbed in lab this week. And we're going to relate it to the color that the solution turns out to be, or the color the solution appears. David?
Does it matter which one of the electrons as a pair goes up?
Good question. Does it matter which one of these electrons moves up? No, because all of these electrons have the same energy.
Okay.
Yeah. So just one of the ones from down here goes up. And it was much simpler, or in many ways much simpler in Chem 400, because we were mostly talking about hydrogen, which only had one electron. But it moved up and as light was absorbed, and it moved down as light was given off. So it's the same process as we talked about last semester. And we're going to do the same calculations. So, and then over here, it turns out that this complex appears blue. And we'll talk about what's absorbed and what appears next. And the last thing, just to be to state it explicitly, this is the ground state because the electrons are in their lowest energy positions. And this is an excited state. And that's important to me because as soon as the light is absorbed and the electron gets promoted, the electron will go back down, and that energy is either given off as a small amount of heat or as other light portions. Question?
Can we add more energy to the point where we can get two electrons to jump up and leave two of the ground states open?
Good question. Can we get two of these electrons to move up? I would suggest, practically speaking, probably not. Because the electron is much happier in its lowest energy state. So as soon as it goes up, it probably comes back down before it can do it again. Practically speaking. All right, well, we're building up our story here. Now we can do d orbitals for tetrahedral. For tetrahedral, a couple things I'll point out to you. So there is splitting, and that is the common theme here. However, now there's 2 on the bottom and 3 on top. And the splittings are given to you, so you don't have to memorize them. We've got the same pictures over here. You can see that in general, the ligands for both of these are farther. And that's why in general, the splitting is smaller. Okay? But what we're suggesting is that for these 3, they're closer, and for these 2, they are a bit farther away. So the same principle applies. If you see a lower energy d orbital, the ligands are farther away. And again, we don't have to know exactly how far, or, but when you're asked to draw a picture, make it clear that one's a little farther than the other. And if your drawing doesn't show it, like all good artwork, say these ones are farther away or these ones are closer.
Do you mean, like you said in general, the ligands are farther from the orbitals, so there's less splitting? Like, you mean like there's less like distance between, or not distance, but less energy, I guess?
Yeah, so I don't know if you remember, but for the higher energy ones for octahedral, so the shapes were different, but these two were actually up top, but the ligands were like right here, so they were practically touching.
Mm-hmm.
And that's why they were way up there, or there was a bigger splitting. In fact, I think my splitting took it off the page. Right? But so two things going on here. One is, same idea, these ones are farther away than from these d orbitals than these are. That's why they're lower in energy, but in general, everything's a little farther away, so the splitting's less.
Okay.
Yeah. Now I'm showing you the splittings for a whole bunch of different setups. The three that you'll be given for sure on the exam are square, planar, octahedral, and tetrahedral, and because that's what we're going to talk about. And what's nice about this is it shows you, it is an O, but it's an O because it's for octahedral. Thank you. I just realized that now. All right, so here's octahedral. You see the splitting's bigger than for tetrahedral. And then you see square planar. And what is the thing perhaps, I don't know, the thing that jumps out at me about this is look at that one way up there. And I don't know, yeah, let me just mention it now because I don't know if we're going to mention it later. But if you remember, we were talking about platinum and cisplatin, and we said that all 8 of the d electrons were in the 4 orbitals, and that one of them was vacant so that the ligands could hybridize with it. It was this one that was super high energy. And so the electrons in square planar typically, or always, fill 1, 2, 3, 4 orbitals and leave this 5th one empty because it's so high energy. Now, one of the things about having 2 coordination number 4 types of geometries is that I have to pretty much tell you what the geometry is. Like in this case, this complex ion is tetrahedral. What is its electron configuration? Is it paramagnetic or diamagnetic? All right, so I'm going to do my electron configurations here. I'm going to over here. I don't know whether you recognize this ion or not. Typically, it's written as SCN. We did a lab with this one. This is the thiocyanate ion. It's written as NCS. Because it is the nitrogen that is bonding to the cobalt. So when drawn like this, NCS, it is the nitrogen that forms the bond with the metal cation. And it still has a minus charge on it. When written as SCN, It is it's a different ligand, actually. Sulfur forms the bond with the metal cation. In either case, they're negatively charged. Since we have 4 negatively charged, and the overall species is -2, cobalt will be +2, or 2 plus. Our cobalt atom has an electron configuration of argon 4s2, 3d7. Take the 2 electrons away in 4s, we get argon 3d7. Okay. And from the previous page, we have the d orbital splitting. For tetrahedral. And now we have 7 electrons to put in, and we put them in 1, 2, 3, 4, 5, 6, and 7. And I think the last question is it paramagnetic or diamagnetic? It is paramagnetic. Next, so questions?
Yeah, for that one where it didn't have the actual the ligands pictured.
Yep.
How am I gonna know if it's gonna be like farther or closer?
Oh, how are you gonna know if these?
Or split farther or closer?
Oh, so if your question is how do I know if it's this or that? Don't worry about that right now.
Just
So-
the ones where they have the actual pictures will have to know.
So what I'm worried about right now is that from the previous slide, that you know that there's 2 lower and 3 higher, which is given to you,
Okay.
right? Not how far they are apart yet. We're getting into that. Marissa?
For these ones, do we need to have this memorized, like how they're split, or will this like chart be given to us with the different things?
When you go to your conversion equation sheets, you'll see that all of the ones for, or I know the ones for octahedral, tetrahedral, and square planar are given. All right. High spin and low spin complexes. Are the next level of complexity. It says elements with 4 to 7 d electrons can have 2 different electron configurations, high spin or low spin. High spin, let me add something to this. And I can't write on this today, but let's do high spin and low spin complexes for octahedral complexes, because that's specifically what we're talking about right now. Those are the ones for which there are 4 to 7 d electrons. And so high spin means as many unpaired electrons as possible. Low spin means as many paired electrons as possible, and lowest energy d orbitals. We get to come back to one of my favorite topics, by the way, 2 competing energies. So one is delta O, which is good because it is octahedral. Although since I just learned this, I can't promise that will always be the correct designator. But for this one it is. Delta O is the electron pairing, Something was not right. Delta O is the crystal field splitting energy. There's a typo. It is not the electron pairing energy. That's going to be P down here. Delta O is the crystal field splitting energy for octahedral complexes. So please fix that. I apologize. P is the pairing energy due to placing two electrons in the same orbital, aka electron-electron repulsion. Okay? And if this is the layout for the octahedral, so this is the D orbital splitting for octahedral complexes. And let's say we have a species with 4 d electrons. There's no doubt where the first 3 electrons go. They go 1, 2. And the question is, where does the 4th electron go? And now is our turn to discuss this. One option is right here. Oh, and this is... And the other option is right there. And so, what I'm saying is, when you put the second electron in the same orbital, there's electron-electron repulsion that we're calling P. And P is some energy. So, if the 4th electron goes here, and the way I'll write that, instead of saying here, or writing here, if the 4th electron goes into the lower energy orbital, P is less than delta O. Meaning that the pairing energy to put them in here is less than the energy to get it up to the top. Electrons always go to the lowest energy places. Now there's 2 places and we have to decide which is lower energy. So if I were to write this, or if I were to say this sentence in words, it would be the energy for, the energy for pairing electrons is less than the energy for getting to the higher energy level. Now we'll go to blue. Blue is just going to say if the 4th electron goes into the higher energy orbital, then delta O is less than P. If the fourth electron goes into the higher energy orbital, then the energy for making that jump has to be less than the energy for pairing. And what this does is this is going to allow us, because sometimes the electrons will go up here, and sometimes they will go down here. And that's how we're going to get information about how far they are apart. Okay, and it won't be numbered necessarily, although sometimes we will relate the size. In fact, we do this quite often. We will relate the size of this jump based on the absorbance wavelength to an energy. It's just the pairing energy term that's harder to put a number to, and that's where we get into the comparisons. Esperanza?
But our rule is still to always fill out the lower energy levels, right?
Good question. Now we're changing the rules,
Okay.
right? And what's going to tell us where the electron goes is sometimes it'll say it's paramagnetic or diamagnetic, or we're going to get to a point where it turns out that if chloride is your ligand, chloride will have a small gap, so the electron will go up here. But cyanide will have a big gap. And so we're getting to that point is, okay, how do we know which ligands have bigger and smaller gaps? And in the end, it's like a puzzle. And you'll have all the pieces to put it together and figure out where the electrons go. But your point is well taken. They don't always necessarily go into the lower energy. And the reason for that is these are actually not that far apart if visible light, not that high in energy, if visible light can promote an electron, then they're not that far apart, and so that's part of the reason. Any other questions about what we've got up there now? Okay. Well, we're going to come back to this, and we're going to talk about this for just the last 2 minutes, mainly because people are going to lab, and I want to say a few words about this before you get to lab. And I said these few words in class on Monday's lab, and it goes like this. Here's the color wheel. It's probably black and white in your book, isn't it?
Yeah.
So, red, orange, yellow, green, blue, purple, or violet. You should label those. And quick poll, by the way. Would you rather have this page in color already and pay 50 more cents for your Hitchhiker's Guide, or would you rather write the colors yourselves and save 50 cents? Write the colors?
Wait.
Would it just be this photo or like other?
You're saying for
50 cents a
Sure.
color page.
Sure.
50 cents a
Yeah.
color page.
Oh, not every page? is it?
Every color page,
Oh.
50
I think that'd be
cents.
cool. How much would that come out to?
Yeah.
You know?
How many
I'm thinking,
colored
like, what else
pages
is
are
there?
there?
Colors might come out.
What's the cost of
Crazy.
the page now?
I'll tell you what,
We need
we'll
all
talk
of that.
more about that.
We can't
Because
vote.
those are the choices I make, and I would love to have your feedback about it. All right, so here's what I have to say about this in my last minute or so. If a solution appears blue, it absorbs orange. And I can't write absorbs orange up there, but please do. And it's always the opposite in Chem 401. And you'll notice there's no like heather greens up here. Those get more complicated. But for our purposes in Chem 401, if you appear purple, it's because you're absorbing yellow. We have a very simple theory. That will help those people who are working through the lab today. And we will pick up there next time.